this is why our talks are at last, so because nobody cares. So I will try to make sure that you care after this. So I'm going to talk about parameterized algorithms for longest paths and cycles about some natural lower bounds. And this is a brand new talk I've never given anywhere, so I'm sure none of you have heard anywhere. And I'm not going to give you an usual, parameterized complexity is this, f of k, no. I'm just going to give you one interesting proof where you will not see parameterized complexity at all. But I will tell you how you can use parameterized to resolve. So it is basically a graph theory plus graph algorithm. So the two most important well-studied problem in parameterized complexity is one is longest path. And what is, you're given a graph G and a positive integer k, you want to check whether there is a path with at least k vertices or not. And there's a similar problem about cycle, okay? A graph G and a positive integer k, and beside the ray contains a cycle with at least k vertices or not. So is the problem clear? We don't need to know anything more. This is all the two problems which you need to know in this lecture. Okay, and here is history for the longest path. So what I mean, so look, you see the running time of the algorithm, right? So you try to find k path in certain amounts of running. Deterministic means this algorithm is deterministic, randomized means randomized. So there is a long history. So people started to make algorithms along this path as early as 1985, and see, parameterized complexity is only defined in 1991 or 89, 90 in a formal way. So people have been trying to make an algorithm, say, hey, can I come with a, so what was their motivation? They said, can I make an algorithm for k path which is linear for every fixed k, right? So what do you mean by linear for fixed k? So if here's k factorial times nm, if you put k factorial to the 100, 10,000, doesn't matter. Still, the dependence on nm or the dependence on the input size is uniform for every fixed k. So in those days, people used to write, oh, it's a polynomial time algorithm for fixed k, okay? And it took us some, at least to me, when I started doing parameterized complexity, it took a lot of time to understand this parameterized algorithm because they didn't write this k factor. They only write order nm because for them k was fixed. Okay? And you had to search through their papers like to see that there is some k factor hidden in column. And there was another algorithm proposed by Hans Bertander, I do not remember the year, I think 87, 88, which was roughly the same time. And it was a big open question in the area that can you come with an algorithm with running time which is like c power k, but why do you care about such an algorithm as c power k? So in 92, 93, Papadimitriou and Yannatakis defined what is called logarithmic classes. So what they wanted to understand is that, okay, vertex cover a long path is polynomial time for 1, 2, 3, 4, but is it polynomial time, say, if I'm interested in, is there a path of length at least log? Now, that question was open for 2-3 years, and then Alan, Lister, and Zwick, in a very fantastic paper, came up with this idea of color coding, and by which they gave an algorithm with running time 5.44 to the power k, randomized, and deterministic c power k. Now, if you substitute k equal to log n, this is polynomial time, and thereby answering this question. But this technique of Alan, Lister, and Zwick about this color coding has been extremely powerful, not only in parameterized complexity, but in many different fields, and its versions are still not completely understood, and people are trying to make algorithms and algorithms based on some of these ideas. So there's a long history, and the reason why I put this up because every development led to a new idea in parameterized complexity. So this introduced color coding. This paper introduced like, if you are wanting to make k, looking at k paths. So if you want to make it colorful, means I have some k path in my mind. I want to randomly color the vertices of my graph so that this k path becomes colorful. In the sense, every vertex has been assigned different color. So Alan and Zwick used k colors and said, oh, this probability is like 1 over t power k because it is on this k path, the total number of possibilities is k power k, and the k factorial of them are good. And if you do computation, 1 over t power k. This paper said, well, if we want to reduce the probability, we might like to use more colors and then see. So this you introduce the idea of, oh, we can use more colors, then we can reduce the probability that we will find, and then they get this. And this NISER and some other people, they said, oh, why not try to take this color coding and try to use like a divide and color. So I only color with just two colors. What is the probability that half the path are 0 and like first half of the path is 0 and this is 1? It's like roughly 1 over to the power k. And then did some kind of divide and conquer. So this introduced divide and conquer. These two paper together. And in Kautis in I think 2008, 7, 8, he came up with a completely different framework and he took these problems and introduced algebra to this. So he basically reduced this problem to monomial testing of some big multilinear monomial testing, and this gives 2.83. Williams refined it even further by introducing group algebras to the field, and he gave 2 power k algorithms for the k. And there's a big open problem in the area, and whether one can go below 2 power k, because going below 2 power k meant that normal Hamiltonian path, which is k equal to n, you can do better than 2 power n, for which starting from Held and Carr, who gave 2 power n dynamic programming algorithm, which we also study in our CLRS book, nothing was known. And in a very beautiful paper, Bjorklund, Husfeld, Kovista, and Kasky gave 1.66k for algorithm. But I must tell you that before that, Bjorklund had an algorithm with running time 1.66 to the power n for Hamiltonian path. And this is a randomized algorithm. We still do not know any algorithm better than 2 power n, which is deterministic for finding a Hamiltonian path. Forget about k, but like just Hamiltonian path in a graph, in undirected graph, we do not know any algorithm better than 2 power n, which is deterministic. So that's a big, interesting open core question. And then later on in 2014, we came up with this. So the big, if you notice that after this was like 2007, and up to for 7-8 years, there was no development in deterministic version of the algorithm. So we came up with this idea of representative set, which was used here in this algorithm. And we found a much more efficient way to compute this object, because when we were trying to decipher through this, we saw, oh, there's an object which has only size 2 power k, but it's just that so if someone gave me this object, I could do much faster, but how to find this object? So we came up with a very efficient algorithm using some pseudo-random variables who could do this work much more faster, and we got slightly more faster, and then we realized that there is some trade-off between how much space and time you can take, and you get 2.619. And I think Mera had a much paper which actually what she did, she took all the deterministic technique and put them together in one. Oh, so say, oh, in this range, or this technique works much better because it has this property, and she combined in a very clever way to get 2.5. So I think this is a current champion algorithm. So this is what I told you in history. So this is the reason why I told you history, because just to tell you the problem which we are going to study has a rich history. It generally leads to a new set of algorithmic techniques, but I will not tell you any of these things. Okay? So here's a puzzle for you. If you get bored in my lecture, here's what you can think of. So suppose you have an oracle who can do the following job for you. So if you ask it, does there exist a cycle of length exactly L? Okay? In an undirected graph, you can do it in 2 power n. So did you get my question? What I say? If you ask this oracle that is there a cycle of length exactly L? Because at most L, can you do it in polynomial time? If I say, does there a cycle of length at most L? You find girth. So, but if you put equal to L, you can show that it is hard. But here you know, and what is my question? You have to solve can you use this oracle to solve longest cycle? What is the longest cycle called? Does there exist a cycle of length at least k? I was not asking exactly equal. It could be that my graph has no cycle of length k, k plus 1, and the only cycles are 2, like Hamiltonian cycle, right? But I'm still telling you, can you find this long cycle, or at least k, using this oracle into problem of it? So, and again, it's a puzzle. So, I mean, if you give this oracle, solving this like a puzzle in undirected graph. And in directed graph, it is not a puzzle, and people didn't know how to do these kind of things. Well, in I think 2002 or 2003, I forget, someone came with k power k algorithm in solar, and then that was our actual motivation to go and look at this web sets and all this, which led to a different set of things. So here's my puzzle. So if you get bored at any point of time, please think about this. It doesn't require anything but assuming that this oracle.
So the oracle will basically for a fixed L, it will say
yes, whether there is a cycle of length L or not in 2 power L.
And I know what L it will answer about. Say 25 or something like that.
L?
I mean, can I say L is equal to 25?
Yeah, you can set anything L equal to.
Oh, I can tell, I can ask.
Yeah, L is like it takes an input L and it will tell you that, but look, I'm only interested in cycle of length k. So you cannot ask this oracle much bigger question. You can only ask, does there exist a cycle of length 5,000k, and it can tell you yes or no. Because you have to solve your at least k problem in 2 power big of k times. So if you ask him, does it is a cycle of length k square, then this oracle itself is going to take you to power big of k square. So you're not. So you are restricted in that way then. Okay. But even if you are allowed this oracle in unlimited time, I mean, still it is not obvious that you can get to power any f of k, because maybe your next path has no, like the longest cycle has no dependence on k. It's like your k is like, I don't know, log n, or I don't know, some very unknown function, and your longest cycle is like n or root n. Okay. So we will need one of these two theorems, which we'll use again as an oracle to solve the problem in some sense. So longest path and longest cycle actually can be solved in time 2.59, which I already told you, and longest cycle actually can be done in 4 power k random distance. But this is not what I'm asking you. I'm asking you simpler, further. And you can actually do deterministically in 4.8. But that's it. Okay, so now we have
k into k cycle is the length of the longest.
no, at least k. Does it is cycle of length at least k? So this is what we need. But length of the longest cycle could be much longer than k. Okay?
So just to understand this precisely, so graph is given, k is a parameter,
Yes.
and you must output the longest cycle. Is that right?
No, you should
You have to
output
decide.
a cycle of length at least k. If your graph has a cycle of exactly length equal to k, you have to output that. But maybe there is nothing starting from k up to Hamiltonian cycle, there is nothing in between. Then you have to output with the Hamiltonian cycle. So a cycle which should be greater or equal to of length k, you are allowed to output. Okay. So people started to use error guarantee parameterization. So if I give you a graph and I ask you, well, if I'm looking for a longest path, what kind of lower bound can I tell that? Okay, if I'm looking for this path, this graph anyway has path of this length. So what is the natural lower bound you can think of on a longest path when I give you an undirected? If I give you S and T, two vertex, what is the lower bound you can say? There must be existing a path between S and T of this length. Shortest path. So exactly. So that is a natural lower bound on any path between pair of vertices. So maybe the graph has shortest path between two vertices, which is too long. Then your question about this asking k may not give you a very meaningful answer. So maybe the natural question should be to ask, hey, I give you 2 points. Is there a path of length which is shortest path plus k? So can you give me something beyond the guarantee which is provided by this graph itself, right? Or one could also have asked, given a graph G, is there a path of length, say diameter plus k? So diameter is nothing but maximum of all minimum shortest path between pairs of vertices, right? So these people had this motivation, and Ivona, Radu, and Holger and Feder, and they define this problem. So you are given an SLP, and you are asking, is there a shortest path of length? There is already the shortest path of length DST, and they are asking, is there a detour or the path of length shortest path plus k? And they showed this problem in FPT. Okay? And what they showed that you have S2P of length, at most k is shortest path, greater than equal to k is longest path, equal to k is exact path, and I already told you kind of algorithm which existed. And so look at this algorithm is bad when k is like the k is less than say DST, something like that. I already told you that if k is much smaller than the shortest path in the graph, then the normal parameterization may not be extremely meaningful. So it is important, or it is interesting to ask these kind of parameterization, like here's the guarantee, can I do much more than the guarantee in using the fact that I'm allowed to use exponential amount of time in the extra which are given. It's not always true. And what they showed that the variation S2P of length at least DST plus k and equal both are FPT using some variations of graph minors, this and that. We will not talk about this. Okay, so what this talk is actually? So now that I've given you 5 minutes, 10 minutes of history, this talk is about longest path in cycle ever degeneracy. So what do we know about what is degeneracy and what kind of lower bound does it provide and what kind of algorithm we are trying to do. So a graph is degenerate if every subgraph h of g has a vertex of degree at most. Okay, so what is the degeneracy of a graph? So then the degeneracy of graph is defined as maximum minimum degree. So look at every subgraph, compute its minimum degree, and over all the subgraphs to take the one which maximizes the degree. So that's the degeneracy of graph. Okay, so it is max over delta h, the subgraph h. Okay? So it's a maximum of minimum degrees over every subgraph. So given a graph G, now we know what the degeneracy of this thing. This is what it will be. So for example, look at this red color. This is a subgraph with a maximum minimum degree among this. What is it? 3. But this vertex could have a different degree in the graph. But if you look at this subgraph, the minimum degree is 3. Right? But if you look at any other subgraph, you will find that there will always be a vertex whose degree will be less than 3. So among all the subgraphs, so next question. Can you find the degeneracy graph in polynomial time? Or forget what. If I ask you, is the graph a degeneracy K? Can you do this in polynomial time? Yes, no.
Find the minimum degree vertex, then throw it out.
Exactly, right? Because that is not a root of x. So you can find this object in polynomial time. So everybody understood that you can find this object very easily. But there are some clever algorithms also. Now, let me ask you a very exercise, because this we ask in our inference tests and all this. If you have a graph of minimum degree d, then it contains a path with at least d plus 1 vertex. Okay? Try it out. I have not used the word degeneracy, I have only word minimum degree. You can also show that if minimum degree is at least 2, then actually you can find a cycle of d plus 1 vertices. And these results are actually true even if a graph is degeneracy d. Then you have a path with at least d plus 1 vertices, and you can also find a cycle with at least d plus 1 vertices. Right? So what is the natural question should we try to ask? If I say here the graph G, can you give me a path which has at least how many vertices? Degeneracy of this graph plus k, because I'm guaranteed to have a path of length degeneracy of this. I can also ask same question about degeneracy with respect to cycle. I know there always exists a cycle of length degeneracy of G. Can you give me a cycle with degeneracy of this graph plus k? Right? So notice, I'm asking slightly more difficult question than just asking k psi, k path, right? Because now I'm asking you, give me a path which is slightly more longer with respect to some structural parameter of the degeneracy. Is the question clear? And the word degeneracy is clear. Okay? Okay. But as I told you, right? So even for k equal to 2, if I ask you, forget about this, if I give you a graph G and I ask you, is there a path of length degeneracy plus 2? And I allow you, look, I'm only asking plus 2, so you are allowed to give me any polynomial time algorithm, right? And that just turns out to be incomplete. Why? It's very stupid and silly reason, but good to know. Here your arbitrary n vertex graph. So I'm giving a reduction from Hamiltonian cycle to this, and I add a disjoint even of clique of size n minus 1. Okay? Clique of size n minus 1. Then notice that the degeneracy of this graph is like n minus 2. So if I ask you, is there a path of length degeneracy plus 2, then that path must exist here. Right? But degeneracy is n minus 2, and I'm asking plus 2, it means I'm asking Hamiltonian path in this graph. Right? Okay. So, I mean, it seems no hope. At least you get the construction, right? So, I cannot even forget about making an FPT. I cannot even make an algorithm running time n to the power f of k if this is a graph which we restrict ourselves. So, we have to do something. So, what was odd about this? This kind of. What happens if you just add connected? So suppose I told you the graph is connected, then can you say this? But then this reduction doesn't work, right? I on purpose added this, right? And I'm going to prove to you that if the graph is connected, actually you can find degeneracy plus k in FPT time. Forget about just polynomial time. So it is just, this is odd. And suppose if I am able to do then you might ask me, hey, then why don't you do one thing, go over each connected component and find this object. But a degeneracy of a graph may not be same as degeneracy of the connected component. So if I go there, but this graph could be very sparse, so degeneracy could be constant, so I will give you constant times some 5 or 10. But that is not a degeneracy algorithm graph. So I cannot do this strategy of, oh, this guy showed me this problem is polynomial times solvable on unconnected graph, then let's go over each connected component and output the maximum length path with this. But that doesn't mean that you are answering the question about degeneracy plus 2 for the win. Okay? So, some caveats. And we can do the same thing for cycling by just gluing one vertex, like just identifying one vertex with this, so that cycle can only live in one part, and you can show that, yeah, it's the same thing works. Okay? So what we proved is the following. Can be solved in this time for connected graphs, right? And as I told you, right, for cycles, you just identify one vertex with this click, and if the initial graph was connected, then this graph also will be connected. But what you can show then, that if I assume that it's two connected graph, which is a very reasonable assumption, so trying to find cycle, because anyway you could go to each block and do stuff. But if you assume two connected, then one can get this kind of FPGA. So at least the result-wise it seems okay that this is what we're trying to do. And the next 25 minutes, I will do a yeah, but one is cycle, other is path. And one I'm saying is for the connected graph because disconnected is. And if you just assume connected for this, you can still show that there cannot exist such an object. That's very simple, trivial reduction. But if you assume it's two connected, yes. So in this lecture, the talk, I'll try to give you a proof for this. I'm not hiding anything. I think I can manage to give you a complete proof. And that's my motivation for next.
So this is slightly out of context. So if degeneracy is 1, so like a tree, then can you do this in like time which is not like checking every path?
That's a very good question. Yes, I mean, I don't know yet, but this is like people try to make say linear time algorithms with this, right? So that will require, that might require different set of tricks and rules. But people also, or you can try to show a lower bound. You can also show a lower bound that no such an object cannot exist meaning ETL set. So now we are able to show such kind of lower bounds also. That if you are asking me to give me linear time with f of k dependence, this is not possible. Okay? So is the result clear? Not saying the proof, but what we are trying to achieve in the next 25 minutes. Okay? So this is what I'll tell you in the next 25 minutes. Okay. So look, I have a graph and I have to find a path of length d plus k where d is some number. So assume that the degeneracy of the graph is say like root n. So now I'm asking you to give me a path of length root n plus k where I'm not allowed to use anything from the root n. I mean, like, I'm not allowed to depend on this root n in terms of computational complexity. Right? So somehow I need to find some structure in my graph where I say, look, somehow if I reach here, then I can use all these vertices in a greedy way or in polynomial time and give you a path of this length. Right? So one needs to find what kind of structure to look for, A, and B, even if I have such a structure, how can I use this structure to get such a path? And if you notice, even if I find a structure, I should be able to tell them, look, if you have this structure, then more or less, you can use all the vertices. Okay? So imagine that somehow we are able to say that, look, this graph had a click of size d. Okay? We had a big click of size d. Okay? Now notice if I have a very big click of size d, it acts as an amazing router. It acts, so somehow if my path somehow reaches here, then I can forget all other paths and say, hey, now that you have reached here, please go and delete everything here, and you are done. Right? So I need to find some structure which will be as good as this click and do this job. Okay? Right? So I need to find a structure in my graph which will act as an amazing router. Okay? So this is one property I would like. That if I reach here, then I'm somehow able to cover all these vertices and go out so that I can say, hey, here's the way you should somehow reach in a nice way on this object. Then you can come up with a path structure which includes all the paths, and hence I can guarantee you that you're having deep reference. Now, why? So somehow I want that objects which I need from outside is bounded by K, because that I will try to use color coding or known techniques to find such a structure. But the moment such a structure exists, which I can check in FPT time, I can use the great routing structure of this object to route this path. So if it is clear, it has also another connecting property. If you forget about one path reaching this, you should have given me, okay, some collections like this, whose length is greater or equal to K here, just this part, then look, somehow I can use, again I can use in some way, okay, so maybe this is one good example, somehow like this, I can still say, okay, go from here, okay, now, maybe this is, okay, go from here, and still follow like this. So what I'm saying is, this path, if you look at the real cycle, how will it look like? Here's my big click. My real cycle came like this, like this, like this, like this. Okay? This is how it might came, we did some vertices. This is how the real path would look like. Now, given this path structure, I would like to say here, somehow I would like to say, oh, these paths gives me some extra from outside, and I want to use this structure and say, hey, given if you have such a path structure, I can use some bits of you and everything from this click, right? And so that I have guaranteed that I have K vertices outside and I have guaranteed that I have D vertices from inside. So even if it's a weird looking path structure, I will tell you that if you give me such a weird looking path structure, I will come with a different path who will have certain kind of connection to this object, and if given me that structure, I can fill that structure with a disjoint paths from this click whose union is every vertex of this. Right? Once I'm able to achieve the structure, then I'm able to do this. And so what will remain to show how do I find this additional structure, and I say, oh, such an object exists if and only if such additional structure exists, and those additional structure like some set of disjoint paths kind of thing, with some terminals here, and those kind of objects can be easily handled with color coding technique in a very standard way. So if you have time, I will go to that, but let's try to understand in this kind of objects, what is the structure which looks like click, which can act like a good router, and I'll prove to you that it is indeed a good router. So is the overall idea of the proof clear? Now we'll try to see how to get there. Okay? And if you look at the proof of some of these structures in classical graph theory, there is one object which comes quite commonly used is the notion of code. And what is the decode of a graph D is an inclusion maximal induced connected subgraph H with delta of H is greater or equal to 2. Minimum degree of this graph is at least. So this is what I mean by decode. And you can see that you can find every graph of degeneracy at least D contains a decode that can be formed. Again, apply the same gradient algorithm. You delete. Eventually you cannot, because every vertex and degree at least D, pick up any connected component that acts like your decode. Because this vertex is anyway not part of your decode, so if you deleted it, it doesn't matter. Right? Eventually what is left, because you are guaranteeing what you are deleting the vertex of degree at strictly less than D. And you know, by definition of degeneracy, there exists a subgraph H where every vertex of degree greater or equal to D. Right? So if I delete a vertex with degree strictly less than D, I'm not going to validate it. Keep doing it. Finally, you cannot do it. Maybe the graph has several connected components, but each connected component is 0. Okay? All good? So, for example, here's my decode in this example, because I found this H, it's a beginning big difference. Okay? So, I want to somehow reach the code, and I want to make this code have properties like click. This is what my objective is. But when you start with, code may not have properties like click. But we can do some nice observations and make it behave like a click. Okay? So what I mean by this? Imagine that K is like your degeneracy. Your K is as big as your degeneracy, or K, then what can you do? If I told you that, oh, K is like D by 2, then D itself, my degeneracy itself, is a parameter of K. Then I can just forget D and say, look, if D plus K is less than some constant times K, then let's apply the good old long cycle algorithm and I'm done. Because D plus K itself is some less than 5K or 10K, I could do this. So I can come to a case where K is is less than some fixed fraction of D. And that is the strategy which we will apply. If D is less than 5K, then we solve longest path of degeneracy using the known result for the longest path. I just check. Each check this. And for such an object, there exists an algorithm. So this allows me to assume the degeneracy is large compared to the K which I am working with. Okay? And then, so from now onward, we can assume the degeneracy is at least 5. Okay, so let's write down some of these assumptions. It might be helpful. And this is a result of Erdos and Garrett, which we are going to use from 1959, who said that every connected n-vertex graph G contains a path with at least minimum of 2 times minimum degree plus 1 comma n. Okay? So whichever is the minimum of these two, you have a path of this line. Okay? So, if my code is too large, I can throw this theorem, because what is the property of code? Every vertex has minimum degree D. Right? So if 2D plus 1 is more than D plus K, then I say, hey, here is my code, I throw this theorem, get my path, and then output. So this theorem will allow us to assume that my code is not too large. If code is too large, you are done because I have thrown this theorem. All these two circles. This is a graph. Okay? So let H be D code of G. If the vertex set of H is more than D plus K, then H contains a path on D plus K vertices. Right? So now I can assume that vertex set of H or the code is at D plus K. Now I'm trying to tell you is this code is actually like a click. Why? K is much smaller than D. Right? Every vertex has degree at least D. So every vertex has small number of non-neighbors. Total number of non-neighbors is upper bounded by K minus 1. Right? So this is almost like a click. Like I have a big object where everybody is neighbor to everybody, but some small number of vertices. Right? So this is what I meant, that we will use this code to get a click-like structure, and once we have a click-like structure, like we don't need exactly the click, but once we have a click-like structure, it will act like an amazing power. And so now we're going to prove that this particular code, so now you can also phrase in a very different object, is that if I have a graph G where every vertex is everybody but at most K vertices, then given some terminal pairs, and if I want certain path structure, I will be able to achieve it. Again, we will apply certain good quality reasonable principle and it will be done. So what I mean by this, right? Let's see. So this is the second which we are in, right? Have at most K minus 2 non-numbers. Okay? This is my only technical slide, so please bear with me. So what I want, so given some pairs, S1, T1, SR, where R is at most K, a collection of pairs about this of H such that S1 is not equal to Tj, but for I not equal to J, S1 is not equal to Sj for I not equal to J, and there is at least one index where SITI is not the same. So I am not telling that S1 cannot be the same, because what I am trying to model, this is exactly what I was trying to do. I was trying to model, here is my code, and here is my cycle node. Okay? So So suppose this is one vertex. So I want to say this is like S1, T1. Okay. Next, I will say fine. So next pair which I'll make is like, oh, from T1 to T2, I would like to go in a certain way. Okay, use yes. Oh, sorry. S1 T1. I'll make, and here for me S1 will be equal to T1. Next guy will be a starting point of this. So next S2 could be equal to say T1, 100 T2, and so on and so forth. Just to record how these paths behave this time. Okay? So this is what it means. Si is not equal to Vj. For all I not equal to. So first coordinate is not equal to any terminals there. But they themselves S1 T1 will be equal, and then at least one pair where S1 is not equal to. Si is not equal to. So they are distinct. So this is not like I have an object and everything like this. This is not. This is all I'm just trying to. And you will see why it is useful. Okay? Then the theorem which I would like to show to you is the following. There is a family of vertexes paths P1 to Pi in H such that Pi is SI Pi path and union of Pi is V of H, that is path covers all vertices. So given you give me pairings, you give me your pairing, I will give you paths between them such that they are pair of vertex joint paths and it will cover all the vertices of H. Which is not like if I give you arbitrary graph and ask you this property that I give you some fixed set of pairings and say, hey, give me a path system on these pairs which covers all the vertices, you may not be able to do it. I mean, forget about covering all the vertices. You may not even have vertex joint paths between these. This is a very famously hard problem. But in our setting, in any such situation and given D code, we can come with such a path system in actually polynomial time. How? So this is what is trying to, this is my H, and this is something which you would like to have. So first let me show you why such a disjoint paths exist. And then I will tell you that I can come up with a path system which will cover all the vertices. Okay? So this is how I construct. I look at the first pair, I go in order. If S1 T1 is the same vertex, then that path is trivial path single. If S1 T1 has an edge, I take that path between edge. What I'm trying to construct at this point of time, that every path between the given pair will be path of length 3. So that it will use only one additional vertex. So we are at some stage and we have constructed some path system. Now let's look at this. Okay? What is the assumption? First, these are two distinct vertices. There is no connection there. But we know how many vertices you have used before. At most k or k minus 1. Now, this H was quite big because if the degeneracy is at least 5k and every vertex is degree at least 5k, then the code has size at least 5k plus 1. Right? You know, if I look at this vertex, how many non-neighbors it has? At most k minus 2. How many non-neighbors it has? At most k minus 2. How many vertices have been used here? Is some k minus 1. Right? And even if you cover it, you will still be able to find a vertex which is neighbor to both of them and which is not used previously. Just use it. That's it. I mean, maybe these numbers you can need to do some tweaking so that this will go through, but this is an idea. I have constructed partial paths. I look at a pair, I say, hey, and this is why I needed the fact that every path which I have constructed here has length at most 3. Because then only I can guarantee that such an object exists. Okay? So I just keep on doing this and I can construct a path. So what did I achieve? That given a code, given a pairing, I can come with a path, disjoint path between them, right? But they may not cover all the vertices. So I need to do a bit more work to make sure that they cover all the vertices. We will again take this path system and construct it inductively and enlarge this path system, and again use Pigeon principle all the time. Okay, so for the proof, you can assume that suppose you are in a situation, you are trying to construct this path system, you have some path system at a point of time, and I ask myself, how many vertices have used up until now? So suppose the number of vertices which you have used up until now is in this path system. Then I am telling you there exists an edge on one of these paths which is a common neighbor. If I find an edge on this path which is a common unused neighbor, I can delete this edge and add this. And I can increase the length of this path. Right? And why am I guaranteed to do this? Because look, number of vertices which is used here is at most 3k. So pick up an edge on this path. How many non-neighbors it has? 2k minus 2. K minus 2. How many non-neighbors it has? At most k minus 2. So there is at least one vertex which is common neighbor to both. So just take this in London. Done. So if the number of vertices which is used in this path system is small, I can do the same trick which I did before. Find an edge which is a common neighbor, remove this edge and take this path. Right? So this is how you can enlarge your path structure. An interesting case is when the number of vertices is more than 3. Okay? Then you go to each of this path or the path system which you have created. Now I will look from that guy's perspective. Okay? I will create some k minus 1 k side matching. What will I do? I will create k side matching using the edges of this path. Like this is one edge. This two edge forms a matching. This edge forms a matching. This edge forms a matching. So given this, I just wanted that my path system is long enough that I can get k side matching using the edges from this path system. Why? Because now I pick up any unused vertex, right? Look, how many edges can it have where it at least misses one neighbor? Okay. So then I will have an edge which is both. I can again do the extension, right? Just basically figure right? So now I created enough matching edges. As I look at this vertex, this guy, look at the edges which it misses. When I say I'm missing at least one of the vertices which is non-neighbor to, then only this k minus 2 such objects. Right? So there will be an edge where he is neighbor to both. I forget this and read out and take this. So it's a very constructive algorithm. So given this structure, using the fact that everybody is neighbor to everybody but at most k minus 2, I can use this to given any terminal pairs come with a path system which covers every vertex image. Right? So this is an amazing property of this router that you go anywhere, you give me pairing, I will give you a completion of these objects in a way that it covers every vertex. And once you have this, you are in a good shape because all I want at this point of time that okay, somehow if there's a path anywhere, let me get him to here and try to use the routing structure of this to use this path, all the vertices of this, because then I have a guarantee that he must have visit deep and he only needs to visit outside. Okay? So now next I need to characterize what kind of this structure is, that if I can find such a structure of small size, I'm guaranteed because of this theorem that I can complete it to a path of length d plus. Okay. So I think I'm over the time. So I'll just conclude in a few minutes. So what you can actually come up with, you can come up with the existing path which uses every vertex of this and uses at most p vertices. So you can prove this, that I'll give you one case and that will, okay? So imagine that this path was completely disjoint from this one. And now this is where I'm going to use the fact that the graph is connected. So suppose this path is completely outside, then I know, pick up some vertex, it must be hitting this path somewhere because the graph is connected. Just go there. At least one of these paths is more than half. Right? If this path is d plus k, then at least one part is d plus k by 2. You take this path, come here, then just you know that given this pair, I can come in and complete it. So done. So this is what I meant, that given this routing structure, if there is a path outside, then I can come with a path of length exactly p at most k vertices outside and using every vertex from inside. Okay? So once you prove this theorem, you could also structure could look like this. Then you try to find a subpath of this with at only p vertices outside and use the rest of things to connect it. So this is the basic idea, that I take this path, somehow try to project it in a small way that the fudge of this path is at most k outside and everything is used completely from inside. And this fudge can be taken care by color coding, like normal color coding. You don't need something very smart there. So this is the whole idea. So I try to give you a full idea from proof. I will not tell you anything more, but you needed to, there I needed to use this long path, but here for the two connected graph, there is a theorem by Dirac which says exactly the same thing, but with respect to cycle. If you have a graph, you have a cycle of 2 degree, minimum degree, 2 times minimum degree plus 1, come ahead. Okay, so And we could also prove that if you are asking that does exist path of length DGBC plus epsilon time DGBC, this is not possible by standard NP hardness reduction. Okay, so let me give you some good open question. So this is a theorem by Edos and Golay. Said every connected n-vertex graph G contains a path with at least minimum of 2 delta G plus 1 n-vertices. But this itself is a lower bound. G contains a path with 2 times minimum degree plus k. I use this to get answer in my setting, but this itself forms a lower bound, so it's an interesting question to ask. It might lead to some interesting combinatorics. Connect with us, we don't know this. Okay? Oh, same question I told you with 2 connected and cycle, you can ask the same question. And for a graph G, average degree is defined by D summation degree by this. There is also a theorem to say that graph G has a path with average degree plus 1, and 2 connected graph G can cycle with average degree plus 1. You can ask the same set of questions with respect to average degree. Again, we don't know anything. And here's my last question. So I was talking about the shortest path, right? Plus A. So what is open there is this D2 question is open for direct data. So if I give you direct data and give you pair of vertex S and T, and I ask you, is there at least a path with length S T of ST plus K in direct data? This we do not know whether there.